A 12-gauge shotgun blast creates extreme kinetic energy. In this test, pellets struck lightweight fabric trousers and failed to penetrate the internal layers. The shells were fired point-blank from 6 meters, delivering a direct impact of lead pellets into the target. The anomaly lies in the material. These plates contain zero Kevlar, no Twaron, and no traditional synthetic aramid fibers. The stoppage resulted from combining a natural hemp bast fiber substrate with a microscopic graphene matrix. Materials engineers used highly conductive nanomaterials to upgrade the tensile strength of agricultural waste, elevating it to ballistic-grade levels. This specific composite bypassed the high costs and heavy physical weight that traditionally plague body armor, successfully halting acute kinetic impact. This empirical result challenges the assumption in defense manufacturing that highly effective ballistic protection requires expensive, heavy synthetic materials. To understand this specific armor geometry, we must look at the operational reality of Thai forestry officers navigating dense, uneven jungle environments on foot. These patrols face a localized, asymmetric threat known as boon pook, homemade tripwire trap guns. Built with simple, low-strung wires, these mechanical traps target wild boars. When a foot snaps the tension line, the crude weapon fires automatically. Because the traps are positioned to hit four-legged animals, the weapon's line of fire is almost exclusively below the 1-meter mark. Standard, torso-centric body armor offers zero protection against a threat factor aimed entirely at the legs. Officers who trigger these traps suffer a specific clinical injury profile: severe, often crippling trauma to the calves, knees, and thighs. This creates a tactical paradox. Lower extremity armor must be dense enough to stop a close-range shotgun blast, but light enough to allow an officer to hike miles through steep brush. Engineering this armor required balancing extreme, localized protection with the preservation of full biomechanical mobility. The ergonomic solution features isolated, modular armor plating. This design avoids continuous, rigid encapsulation that impedes a ranger's movement. Protection is restricted to 3 highly specific targeted strike zones: the side thigh, the knee, and the side calf. The figure-8 design of the knee plate serves a precise biomechanical purpose. It allows the patella to articulate freely during a bend, without the rigid edge of the plate digging into the officer's shin. By separating the thigh and calf plates entirely, the design eliminates friction and prevents muscular fatigue during the repetitive, high-angle stepping required in jungle terrain. This minimalist geometric efficiency drastically reduces the overall weight of the garment, especially when compared to the heavy leg armor used by explosive ordnance disposal units. These plates are integrated directly into standard-issue camouflage trousers. This maintains visual uniformity while keeping the officer's physical profile low. While this modular design solves the human mobility constraint, it transfers the entire ballistic burden onto the physical density of those small, isolated plates. The structural foundation carrying that ballistic burden is a plant, hemp bast fiber. Extracted from the stalk of the plant, hemp bast fibers possess high tensile strength and natural physical resilience. However, raw natural cellulose fibers cannot dissipate the acute kinetic energy of a close-range shotgun blast. Bridging that gap requires a reinforcing nanomaterial matrix, high-purity graphene powder. Graphene is a 2-dimensional carbon allotrope. It is structurally 200 times stronger than steel, yet it contributes virtually zero additional mass to a composite. Infusing the hemp with graphene restructures the mechanical properties of the plant fiber, creating a hyper-rigid microscopic lattice over the flexible natural base. The graphene powder adheres chemically to the treated hemp fibers, ensuring a perfectly uniform distribution of the carbon layer throughout the material. By combining these two structures, materials engineers successfully upgraded a sustainable agricultural product into a hyper-advanced ballistic composite without adding physical bulk. To build the plates, multiple layers of this graphene-coated hemp are stacked together and infused with a binding epoxy resin. But the layers alone are not enough. Solidifying the composite requires extreme industrial hydraulic compression. Immense pressure serves a strict mechanical purpose. It eliminates microscopic air voids and forces the epoxy resin to permanently interlock with the graphene-coated fibers. This step is critical because it prevents delamination when the plate is suddenly struck by high-velocity impacts. Returning to the initial test, when 9.40mm lead pellets travel at high velocity, striking the hardened surface of this newly compressed plate, the high tensile strength of the surface instantly deforms the lead projectiles, flattening them and robbing them of their aerodynamic penetration power. Because the projectiles cannot penetrate, their kinetic energy is forced to disperse laterally outwards across the rigid horizontal layers of the plate, rather than tunneling inward toward the officer's leg. The hydraulic compression transforms the stacked natural materials into a unified kinetic energy sink. It safely halts a lethal threat at a fraction of the weight of solid steel. Protective gear is useless if it is heavy, uncomfortable, and left sitting in a locker room. To test operational viability, researchers gave the prototype trousers to 100 actual forestry and national park officers to wear during active jungle patrols. The resulting data was evaluated using a rigorous academic framework known as the Technology Acceptance Model. This bar chart displays the survey results. Out of a maximum score of 5, the gear scored 4.58 for ease of use and convenience, 4.41 for perceived safety, and 4.20 for ease of cleaning. The high perceived safety metric is vital. It indicates the gear successfully reduced tactical anxiety in the field, improving the officer's operational focus. The statistical analysis also revealed that older, more educated officers demonstrated the highest rates of technological acceptance for the new armor. Theoretical physics mean very little without user compliance. This data proves that the module geometry successfully bridged the gap between lab-tested safety and real-world wearability. There is one final engineering constraint that often kills government deployment of new technology: production cost. Specialized synthetic aramids are notoriously expensive, while raw agricultural hemp is cheap and abundant. This pie chart breaks down the prototype's total production cost. The entire unit comes out to 4,400 Thai baht, roughly $120. The vast majority of that budget goes toward labor and assembly, with only a fraction required for the raw materials. A $120 unit price enables wide-scale departmental procurement, making it possible to provide these trousers to every patrol officer. By rejecting traditional heavy torso armor designs, engineers solved a highly localized asymmetric threat. By synthesizing natural macrofibers with atomic 2D matrices, they created an entirely new tier of sustainable tactical equipment. Advancements in protective materials involve re-engineering sustainable natural resources with nanomaterial precision to address specific human constraints.